Hello everyone, welcome to our channel. So let's get started. We are taking one more question asked in the EC GATE exam. All right. So I may state the question. In the feedback system, in the feedback system, so they given the our plant Gs equal to 6 pi s into s plus 1 into s plus 2. So plant is our since this feedback system and feedback transfer function means Hs is equal to 1 here. So our open loop transfer function is completely would be same equal to Gs 6y into s plus 1 into s plus 2. Alright. So here this is type 1 system and they are asking Rs and they are saying that they are saying that they are Rs by s Es are the Laplace transform of Rt by t and Et respectively. And if input Rt is a unit step function, then which option would be correct? Okay, so how to solve this question? What's a useful data is required to solve this question? First, we should know the you know our final value theorem. Okay, so here basically final value theorem states that limit t tends to infinity any function, like for example take ft, and limit s tends to 0 in Laplace domain. So here s into fs. So point is that here when t tends to approach to infinity, then we need to find out the final value any function. So in this is time domain we can find out, but in a differential equation it's difficult to solve and find out. Okay, so rather than go for a differential equation, we can go for an algebraic equation and then easily we can find out. Okay, but point is that in final value theorem we cannot apply directly in all transfer function. First we should ensure that given transfer function is stable or not. Okay, so let us for which we can find out the apply the final value theorem. So here this is one case, like for example this is a completely left hand side. Okay, yes plane. So here you can see in case of left hand side. Okay, so take like for example the pole is like 1 plus s plus 1. So in this case if you apply like in a time domain, it will be minus t ut. Okay, so here our find out then it will be coming like that, right? So e the power 0, so it will be going to, so when t approaches to infinity its value will be 0. So here final value will be 0. Okay, in time domain actually we can see once t approaches to infinity. Let us apply the final value theorem here in s domain. So like s tends to 0, so s into fs. So here s into fs s plus 1 by s plus 1. so it also going to 0. So this also gives the correct answer. Okay, so when system is stable, then our final value also gives the correct answer. Okay, and take one more reason, like if you pole like lie in the our, for example, right hand side. Okay, so like pole take like for example take pole is s minus 1. Okay, so pole is right hand side, we know system unstable, but if you apply in time domain, what is the answer? T ut. So here you can see it goes to, once t approaches to infinity, value get blows up, system get blows up, value going to high value here. Okay, so here we find out the our final value theorem here. So in this our final value does not exist, right? We know that final value does not exist because this value going to infinity. But if you find out the here final value theorem, okay, so let's apply. So it will be 0 answer. So this is a incorrect answer. Okay, take one more case, like if you pole lie in the imaginary axis. So you know this is we are excluding the origin. Okay, so here should take like 1 by a square plus 1. Okay, so plus j and minus j. So you know imaginary term will give the oscillation. We know this because this introduce the sine and cos term. Okay, so if you give some how it will looks like, it will be coming like that, right? Sine and cos like that gives the oscillation. All right, so point is that in this our final we know final value does not exist because it oscillates. We don't know positive value, negative value is oscillatory. So in this case also is not, final value is not exist, right? But let's apply the final value theorem. So it coming the 0. So this also is a gives the incorrect answer. Okay, and then if you apply here like pole lie in the like origin. Okay, so let's say like pole is 1 by s, 1 by a square and 1 by sq and so on. So here let's apply the our you can see also system type of the system equal to the number of pole at origin. Okay, so here like 1 by s, let's apply the final value theorem. It gives the 1, or we can say finite value. So in the case of type 1 system, it gives the finite value, or and if you type 0 system, then like this is s plus 1 type 0 system, then it will keep the 0 value. Okay, type it gives the 0 value, and type 2 system, then This also give the zero value. Okay, so point is that if system type 2 or more than that, our final value gives the it gives the infinite value here, na? If type more than the type 2 or more than, then it gives the infinite value, right? So if here we can see if type 2 or more than, then final value gives the infinite value. Okay, so which gives the correct answer, right? So here we can see what's the reason we can apply the our final value theorem. This region means including the origin poles and left of the spline. Here we can apply the final value theorem, and this region including the j omega axis excluding the origin. Okay, so this thing we can see this is big, we cannot apply the final theorem because it gives the incorrect answer. Okay, so with this introduction, let's solve our given question. So they given the question GS, they given actually 6y s into s plus 1 s plus 2. All right, and let us draw the our block diagram. GS, okay, this is our input RS in Laplace domain, everything I am writing here. This is output. Okay, so this is negative feedback, and here we are putting unity feedback. Okay, HS is equal to 1. So let us solve for and they are asking the ES means error signal. Okay, so point is that in case of error signal, let's drive the transfer function for error signal. So ES versus divided by RS, this is transfer function we need to apply here. Since this is block and simple, easily we can find out just applying the algebraic. ES is equal to how much? RS minus, this is a feedback directly we are feeding to our output. So here is a CS output. Okay, and CS they giving here bias, right? Okay, they presenting here output is bias, so let us write bias only, so there will be no confusion. So bias, so it will be bias. So here you can see this ES input means error signal, and this is GS plant, and this is our bias. So bias is equal to ES into GS. All right, so here ES into GS, so E, so finally we can get our transfer function ES equal to 1 by 1 plus G. Yes, since here HS is not there, that's why putting here 1 by 1 plus G. Otherwise if you HS there mean feedback transfer function there, then we can say 1 by 1 plus G into GS into HS. Okay, here HS is equal to 1. All right. So we determine we already derived our uh, error signal in terms of input, but point is that we can only error signal we can only find out once our system get settled, system is stable. Okay, so for this, first we need to find out the characteristic equation and ensure that our system is stable. Okay, so here you can see what is our characteristic equation. So let's find out the transfer function. Ts gs equal to gs plus, because this is our unity feedback system, this is negative feedback system, that's why constant positive here. Generally in the case of a stable system, generally we apply the negative feedback system. Okay, so all right, so gs is giving 6 plus s into s plus 1 into s plus 2 y 1 plus 6y s into s plus 1 s plus 2. So it's coming 6y. Okay, so let's find out. Let's all simplify. So it's coming 2s, 2s, and 1s. It's coming 3s plus 2 plus 6. Okay, so 6 s cube plus 3s square plus 2s plus 6. All right. So what is the characteristic equation? You know the characteristic equation is our transfer function denominator polynomial. Okay, characteristic polynomial is a denominator polynomial. Okay, so characteristic polynomial, let us say ps equal to denominator polynomial is s cube plus 3s square plus 2s plus 6. All right, so here let's apply the our Routh-Hurwitz criterion. Okay, so what Routh-Hurwitz criterion says that in Routh-Hurwitz table, this first column, all uh, term, there are no sign changes. We can say system is stable. There is no pole would lie in the uh, right hand side of the S-plane. Okay, and so let's apply the let's form the our Routh-Hurwitz table. So here you can see order is 3, so we can say S3 s power 2 1 and s power 0 constant term. Okay, so sq plus this is power 3, right? So alternative we can fill this row actually. So here is coefficient 1 and then 2, s square coefficient 3 and 6. So how to fill other remaining row? So just multiply this 3 into 6, 3 into, I am here writing a step by step, 3 into 2 into multiply 6 into 1 divide by again 3 this term. So this answer would be 0. This also 0. Okay, there is no term. So here it's forming the entire 0 row. So what is the significance? Uh, how to uh, fill other term? Because so for this we need just take above a row, and this also called the auxiliary equation. Okay, a auxiliary equation. So here s squared power 2 plus 6, this is auxiliary equation. and take a derivative of other equation, you will come the 4s. So 4s means here we can substitute 4 and this is already 0. Okay, so 4 into 6 minus 3 into 0 divided by 4 is coming the 6 here. So here you can see there is no pole, all term is positive, 1 3 4 this column, first column. I am only concerned about the first column of the Raut-Hurwitz. Okay, so Raut-Hurwitz table. Okay, so here you can see in the first column there is no sign changes. Okay, all signs same. So one thing clear, there is no pole in right hand side of the plane. But here one zero row, entire zero row exists actually. Okay, row of zero exists here. So it means that what is the situation when this entire row would be 0 in a Raut-Hurwitz table. Just let us what's the condition actually when this entire 0 can exist here. So here basically if pole with respect to the origin, okay, is symmetrical, can we say like that this is origin actually here. Okay, this let us say this is plane. So like take one pole here and take one pole here, for example take -2 and +2. So this is a symmetrical with respect to the origin. Okay, this is either one case actually this can be there, and second case this case also can be there. This also with respect to the origin. Okay, so be symmetrical with respect to the origin, and last case can be like that also. Okay, like this is for example 2 plus 2j, this is minus plus sorry -2, right? So -2 plus -2j, this is a +2 plus 2j. Okay, this is minus +2 -2j, so it's symmetrical. Okay, so it means since this in our given question point of view, this first case and third case is not there. Okay, because there is no pole right hand side, but second case is possible. Okay, means pole would be lie in the j omega axis. So once pole in right in the j omega axis, we know that when pole lie in the j omega axis, so you can see either power minus imaginary term will introduce the our sin and cos term. Okay, so our system response would be oscillating. Okay, we no need to find out the exact oscillation, exact response. Only we should know whether the system is stable or oscillatory. Okay, so first we have understood that for a given question, system is oscillatory. Okay, so system is oscillatory. So in this way, we cannot find out the error because response is not stable. Response doesn't get settled, so we cannot find out the ES. So ES here would be in oscillatory, does not exist, and it will be oscillatory in nature because our response will be oscillatory. Okay, so here no need to solve the further applying the like yes and find out. So our answer would be D option is correct for this question. Okay, okay, let us for sake of completeness let us apply the our formula, but point is that if you apply the formula here the answer will be we will end up the incorrect answer because here we cannot let's see. Okay, So ES is equal to RS by 1 plus GS. So limit S tends to 0, this is ET, T tends to infinity. Okay, so limit, so here S into ES, so S into 1 by S by 1 plus 6 by S into S plus 1 S plus 2. So how much value coming actually? So S cancel out, will be coming, let us solve, simplify. Basically we cannot need not to apply the final value because we know system unstable, so system oscillatory, so here we cannot find out the error signal actually, so it is oscillatory nature. So S plus 1 S plus 2 plus 6, so it will give the 0 answer, which is incorrect. This is the incorrect answer actually. Okay, so in case of our final value theorem, understand, we should ensure that whether given system is stable or not. Okay, but in case of a pole lie in the origin, this also gives the incorrect answer. There's no any problem. Okay, so in this red region, this is, here we cannot apply the final value theorem because it gives the incorrect answer. Okay, here it includes the our j omega axis excluding the origin. Okay, and completely right side of the S plane. Okay, so this thing, we in this region we cannot apply the our final value theorem, and here left of the S plane, and if you pole lie in the origin, this thing it gives the correct answer. Okay, so hope you understood. Okay, so that's all. So thanks a lot.